Okay, welcome. Welcome, everyone. Everyone find a seat. Thank you so much for coming. Great to see you all on a lovely fall evening. And we have quite a treat for you this evening. It's a great pleasure to introduce our speaker. Oh, by the way, I'm Mike Walter. I'm the director of the Earth and Planets Laboratory here at Carnegie Science. And this is the first of our neighborhood lectures for the fall time. Anyway, it's a great pleasure to introduce our speaker, Dr. Phil Plait, AKA the Bad Astronomer. And Phil got his PhD a long, long time ago in a nebula far, far away at the University of Virginia, where he worked on supernova. After that, he went on to the Goddard Space Flight Center, where he worked with one of the first people working on the Hubble telescope, I think on the Space Science Imaging Spectrograph, Space Telescope Imaging Spectrograph, looking at very faint objects in the universe. After that, he was at Sonoma State College in California, where he began, I think, his passion for public outreach and education. And since that time, he's been a freelance public outreach expert, and you might see him on Discovery Channel and various other public venues. And tonight, Phil is going to talk to us about Under Alien Skies. This is his most recent popular science novel, or pop science book, excuse me. The first one was Bad Astronomy. The second was Death Under the Skies. And the third is Under Alien Skies, all available on Amazon.com. That was not a paid-for announcement. Anyway, Phil, it's a real pleasure to have you here tonight, and take it away.
Stand up?
You should stand up and...
All right, is this on? Yep. You can hear me? No, of course not. Here, let me. How about now? I can do this. Does that help? Is it working? I hear an echo. Sure, I'll just keep talking. So, it's a pleasure to be here. I've been here before, not to speak, but just because I've known Mike's wife for a long time. We got our PhDs together at UVA, actually. That's how I know Michael is through Peru. Came here to visit once, and it was a lovely place. And when they asked me to come up and give a public talk, I was like, sure, I love this stuff, so I'd be happy to. And I can hear my voice really clearly now, so I can stop being extemporaneous. Excellent. So I am an astronomer. I've worked on Hubble and Cosmic Background Explorer, and done public outreach for a bunch of other NASA missions. Did research for a long time. And as much as I enjoyed it, I discovered I liked talking about this stuff better. I like going out and showing people stuff. I am happiest under a dark sky with my telescope, and I've got the bona fides. I know what end of a telescope is which. And one of my favorite things is showing people Saturn for the first time. If you've never seen Saturn through a telescope, you need to fix that, because it's amazing. And a lot of astronomers and astronauts, when you ask them what got you started in this, it's 50-50. It's the moon. They saw the moon through the telescope, or they saw Saturn. For me, it was Saturn. I call it a gateway planet. Once you get that, you're hooked on astronomy. And when I'm out showing people the sky a lot, a question I get, very common, is this what this thing would look like if I were there? And a lot of times the answer is, well, yeah, I mean, the moon looks like the moon. It's not trying to trick you. It's a big gray rock in the sky. But some other things would be different. Giant gas clouds, nebulae, where stars are born. Turns out, if you're inside one, it doesn't look like it would through a telescope. And in fact, there are a lot of objects like that. And to actually go to these things, if you were to actually go to the moon and stand there, what would you see? And it turns out, not always obvious to people. And so many, many years ago, I pitched an article idea to Astronomy Magazine. I said, I want to call it Under Alien Skies, and I'm going to give 3 sort of you are there stories. You're standing on a planet orbiting 2 stars. What is that going to be like? And they dug that. I wrote it. They printed it. They even paid me, kind of. Don't try to make your money writing for magazines. Little life advice there. And years and years and years later, I'd always thought the whole time, there's so many more things I could do with this. It'd be a great book. And then, gosh, 20 years later, I finally wrote the book. And so the idea of the book is you are there. You are visiting the moon. You're visiting Saturn. You're visiting Pluto. And you're on a ship or you're standing there. What do you see? What do you experience? What do you feel? What does it smell like sometimes? It turns out it's just, the inside of a spacesuit that 100 people have rented before you. So you can guess what it smells like. And it was so much fun. I wanted to develop a talk based on the book. I couldn't fit every topic in there because it would just be me narrating the book, and that would take too long. So I've narrowed it down to just Saturn. For the purposes of the next 40 minutes or so, I want you to think that you are some number of years in the future, call it 100, it doesn't matter. And you have saved up for a long time and you have bought your tickets to get on a spaceship which is going to take you to Saturn. So at first you don't see anything. Sky is kind of black. It does that. I'll make sure this is going to start. This is what happens when you fiddle with a talk right before you give a talk. There we go. Saturn is the second largest planet in the solar system. It's only smaller than Jupiter. So it's immense. It's 9.5 times wider than the Earth. And if you do that math, it's about 1,000, very roughly, times the volume. You could fit several hundred Earths inside Saturn. It is an immense planet. For a long time on Earth, all you can see of Saturn is a dot. It's just a pale yellow dot in the sky. It's too far away to really see any details. Once the telescope was invented and people started looking at it, like say Galileo, he could see that it wasn't round. It was kind of elliptical and weird looking. Galileo said it had ears on either side of it. And then as telescopes got better, they realized, oh, this isn't, it's not actually like an ellipse. It's a ball with some sort of ring around it. And as time went on, we learned more and more about it. From the ground, even with powerful telescopes, the view isn't so great because we're sitting underneath an atmosphere. But if you're on a spaceship and you're approaching a planet, it's going to look a lot more interesting like this. So as our captain takes us towards the planet, we're coming in well over the plane of the rings. And what I mean by that is that the rings are extraordinarily flat. And so we're coming in at an angle so that we can see them spread out. From Earth, when you look at Saturn, sometimes Saturn is tipped. It's tipped over like the Earth is. Earth has that 23.5 degree or 24 degree tilt. Saturn's is about the same. I want to say 25 degrees, but the exact number is not important. It is tipped over relative to the sun. And so sometimes when we look at it, it's tipped toward us and we see the rings all spread out. Sometimes it's tipped away and we see the rings tipped the other way. And twice every Saturn year, Saturn takes 29 years to go around the sun. So every 15 years, call it, we see the rings edge on. It happens to be the way the geometry is set up. And they look like a thin line going across Saturn, taking us out of the spaceship and back to Earth in 2024. That's going to happen next year. So right now, if you look at Saturn through a telescope, the rings are very, very thin. You can barely see them. And they're going to get thinner. And is that me? Am I echoing? It's the Saturnians. They don't want us there. It's interesting when you see Saturn and its orientation is like this through a telescope. It's very bright to the eye, and then when the rings are more edge on, they reflect so much sunlight. They actually generate a lot. They're much of the light that you see from Saturn is coming from the rings, and so when the rings are edge on, Saturn is noticeably dimmer. So I'm looking forward to seeing that next year. Just seeing Saturn going, oh wow, look how dim it is. That's what excites an astronomer. I'm sorry. So we're approaching the planet now. Most of the moons orbiting Saturn, and Saturn has a lot of moons, and they're all really strange. We're going to get a taste of that here tonight. Most of the moons orbit Saturn in the same plane as the rings. So if you were to see Saturn with the rings edge on, and the rings orbit right over Saturn's equator, and I'll talk a little bit about that a little bit later, then all of the moons would be sort of lined up in that same plane. However, not all of them do. And a couple of them are actually up pretty high. And the first one that we will be approaching is Iapetus. Iapetus has been known since the 1600s, maybe 1700s, so many centuries, as a little point of light orbiting Saturn. It's pretty far out, 2.5 million kilometers is what I'm thinking. I'm sorry if I use metric. And if you want to just think of kilometers as miles, you're fine at the 2.5 million scale. The difference, it's a long walk either way. So it's fine. It's not very big. It's smaller than Earth's moon. It's a few hundred kilometers across. And it's weird. And that's something you're going to hear a lot, because everything about Saturn is weird, and the moon's even more so. It's mostly ice and rock, which is true for most of Saturn's moons. It's got that whopping big crater right there. That is a running theme for Saturn's moons, and I'll get back into that in a minute. But it's interesting that you will see a gigantic crater on almost all of its moons, but they don't get any bigger than a certain size typically. And there's a reason for that, which we'll get into, and it's cool. And we didn't know this until spacecraft started going out there and actually seeing these things up close, because you could never hope to get a view like this from Earth. There are a couple of weird things about Iapetus. One is that it's got this, it's bright and reflective on one side, and the other side is much darker. You can only see a little bit of it there. But it turns out, yeah, it's got like a bright side and a dark side. And this was a big mystery for a long time. There were a lot of different ideas for how this might work. Some ideas came up in the 21st century. Now, of course, these days, of course, we know the answer, and I won't bore you with the details, because it's the future, and we know that now. I'm just reminding you that that's the running gag of this talk. Thank you, whoever that was. But that's not the most peculiar thing. Actually, again, in 2024, don't know why that is. It's just peculiar. There are some ideas, but nobody's really 100% sure. But that's not the really strange thing about Iapetus. The really strange thing is that it's a gigantic space walnut. It's got this weird ridge running all along, and it's right on the moon's equator. What is this? This was a complete shock when it was first discovered by spacecraft passing by this moon. That ridge is immense. Some of those peaks are 20 kilometers high, so multiple times higher than Mount Everest on Earth. And sometimes that ridge can be a couple of dozen or even more kilometers wide. So it runs all the way around the moon. What is this? A lot of ideas. There was this idea that maybe when the moon first formed, and again, mostly water, ice, and rock, it was molten, spinning really rapidly, and then as it cooled and the crust shrank, it kind of crinkled up, and right around the equator, because of all the forces and everything, you got this gigantic mountain range. It's like, well, that doesn't quite answer all the questions. Another idea is that a gigantic comet or asteroid, or maybe even another moon, whacked into Iapetus at relatively low speed, but it was still a colossal impact, blasted a huge amount of material into space, which then fell into a flat ring orbiting Iapetus, and then that ring eventually collapsed down and basically rained down rock and ice onto the moon to build up this mountain. That would be a catastrophic event. After a huge impact, to have all that material raining back down would be disastrous. Maybe that doesn't answer all the questions about what's going on here. I kind of like the idea that you had a ringed moon orbiting a ringed planet. But then we found out, and we'll talk about this too, that the rings of Saturn haven't been around forever. So actually, this may have had rings before its host planet did. Here's another angle on it. We're in our ship coming down over the moon, And you can see that is a mountain range. It is really, really big. It's not like even individual peaks. There are some places on it where it's broken up a little bit, and it looks more like a mountain range. But in general, yeah, it's more like a fin than anything else. Very, very strange. Well, now we're going to come back down from our high angle and come in towards Saturn on the plane of its rings. And now we can see it where the rings are sort of edge on. And there are a few cool things about this view. One is that you can see a few of the moons. We're going to pass by a couple of these, including that peach orange fuzzball there. That's Titan. You can see the shadow of Titan on the planet, which is kind of neat. The rings are very thin. Now, they're huge. They are 250,000 kilometers end to end. For scale, if you put the Earth at one end of the rings, they would stretch something like 3/4 of the way to our moon. So, and it took the Apollo astronauts 3.5 days to get to the moon. So this is an immense structure, and yet they're very thin. And I ask people sometimes, how thick do you think they are? They're 250,000 kilometers across. How up and down, how thick do you think they are? Any number. 30 feet. Somebody's read my book. No, let me be the funny person here. That's actually correct. A lot of people say, I don't know, 100 miles or 10 miles or whatever. And it turns out, no, now in a lot of places they are on that scale, a kilometer or two thick. But in some places they are as narrow, as flat as 10 meters, 30 feet. So that's not much taller than this auditorium. And yet they are 250,000 kilometers across. Kind of amazing. To scale, they are flatter than a piece of paper. If you take an 8.5 by 11-inch piece of paper and expand it up to the size of Saturn's rings, that paper would be thicker than those rings, which is amazing to me. That kills me. I love that idea. Why are they so thin? Well, it depends on how they formed. It may have been two moons collided. There are a lot of different ideas. Maybe a moon was disrupted by an asteroid impact or something like that. It was a very icy moon. It shattered, blew all of its material into space. Saturn, its gravity, well, as these things are sort of orbiting Saturn every which way, if two of them collide at an angle, because of the way this kind of stuff works, that will tend to flatten out the cloud of debris. You're sort of averaging all of the random impacts, and you wind up getting the cloud of debris will flatten out. There's more going on here. I'm going to skip to another thing and come back and say, another weird thing about this picture is Saturn's not a sphere. And you can see that in this picture. It is wider at the, oh boy, it kind of actually looks like a circle from this angle. But when I come in like this, oh yeah, look at it, right? It's much wider at the equator than it is through its poles. And there's two reasons for that. One is that Saturn is incredibly low density. There's not that much stuff packed into that gigantic ball. So density is just basically how much, I want to say mass per volume. I don't want to be confusing, but if something is this big and has a certain weight, and then something else is this big but weighs 5 times as much, this is denser. This has more material packed into it. And you have an intuitive feel for that. If you pick up a rock and you pick up a chunk of iron, right, the iron weighs more, it's denser. Ice is lower density. And we measure density typically in grams per cubic centimeter. And it turns out water is 1 gram per cubic centimeter. So that's a great unit. You could just say the density of something is 1, and astronomers know that that means 1 gram per cubic centimeter, which is the density of water. That's cool, because ice is less dense than water, 0.8, 0.9, something like that. Rock is 2 to 3 times the density of water, and metals tend to be 8 or 9 or sometimes even more. So if you can get the density of an object, you can right away kind of know what's in it. And Saturn's density is actually 0.7. It's less dense than water. It's gas. It's mostly gas. It is a gas giant. And so it's actually got a core that is more massive than the Earth and probably has lots of metal and rock. But above that is mostly gas and liquid, which is very low density. So when you average all that stuff together over Saturn's immense volume, you find out its density is 0.7. Well, that means if you had a bathtub big enough and you put Saturn in it, it would float, but it would leave a ring. Ah, yeah, I know. That is like literally the oldest astronomy joke there is. It's not my joke. So that's one thing that is why it's flattened. It's also spinning incredibly rapidly. A day on Saturn lasts less than 11 hours. It's just about 10 hours, close enough. So it's huge, remember? It's almost 10 times wider than Earth. It's spinning over 2.5 times faster than the Earth, something like that. And it's very low density, which means there's that force outwards, that centrifugal force outward. And it distorts Saturn into a flattened sphere, what we technically called an oblate spheroid. And I just like saying that. It sounds very sophisticated. And so you can see that in the pictures. You can see it through a telescope too. That's also why Saturn's rings are flat, because there's more gravity in the equator of Saturn than there is above and below the equator. So if you're orbiting something, I say more gravity. I'm trying to sort of synopsize a very complicated physical situation involving the tidal force and all this other stuff. But basically, if you're a particle orbiting Saturn, you feel a tug on yourself down until you're orbiting over the equator. And that's why Saturn's rings are so flat, because it's bulging out like that. Its gravity's pulling stuff down into the equator, the equatorial plane. So that was a lot of words to talk about why Saturn's rings are flat. I could have just said they're flat because of gravity, and we'd be done. I love the sound of my own voice. So as we approach, and we're almost in the plane of the rings, this is a good shot because you can see the shadow of the rings on the planet. And again, the planet's not solid. What you're seeing are the tops of clouds in its atmosphere. So if Earth were perpetually cloudy, it would be sort of the same thing. And you can see there's some very soft banding that you can see, the ring shadow, and then that thing up there. It turns out Saturn has weather, and sometimes in the summer, especially in the northern hemisphere, some stuff will bubble up from the interior of the planet, bubble up to the tops of the clouds and spill over. It's a gigantic storm. And in Saturn, they're huge. The head of that storm is, Earth size. So imagine, there's a hurricane bearing down on Florida. Now imagine something like that, but it's the size of the entire planet. That's what's going on here. So this stuff welled up and bubbled out. And then as Saturn is rotating around and the winds are blowing on this storm, it blows the storm around the planet. And you can see it blows all the way onto the dark side, comes all the way around the backside, and you can see it coming back underneath the storm there. So it wrapped all the way around the planet. So that's a storm that is, over 100,000 kilometers long. Phenomenal. Saturn doesn't do anything small, at least not the planet itself. Now, okay, we're still heading in. We're heading in towards the rings. We're going to pass by another weird moon. This has my vote for the weirdest moon in the solar system. This is Hyperion. It looks like a giant ball of styrofoam that somebody has punched. And it looks like that because physically, it is a giant ball of styrofoam that somebody has punched. Sometimes things are easier than you might expect. It is very, very low density, incredibly low density, so much so, and it's mostly ice, mostly water ice. And I say water ice because at this distance from the sun, which is over 1 billion kilometers, most gases on Earth are frozen. Carbon dioxide, carbon monoxide, ammonia, methane tend to freeze at these temperatures. Maybe not carbon monoxide, but still, a lot of gases are frozen. So this is mostly water ice. Even so, by getting how dense it is, by measuring that in various ways, they found out that it's half the density you'd expect, even if it were just ice, which means that it's porous. It's mostly empty space, in the same way that if you take a box and fill it with styrofoam peanuts, right, there's a lot of room in between the peanuts, a lot of voids in there, a lot of space. Now, there's no air in space, so it's not like this thing's filled with air, it's just a vacuum. But this thing is porous, like a sponge. It turns out it's mostly ice. It's 300 kilometers end to end. It's big. But it probably has been whacked over and over again by other objects, asteroids, comets, maybe other moons. that have possibly even blown it apart and then had its gravity pull it back together, or have hit it hard enough to sort of shatter it in place. Either way, it's basically a gigantic pile of ice shavings, basically held together by their own gravity. And that makes it look weird. Impact craters don't look like what we're used to seeing on Earth's moon or some of the other rocky moons of Saturn. There's no atmosphere on this thing, so everything that hits it. Nothing burns up. They all come down and hit. So the craters are really deep. They have sharp edges. There's that immense crater, this huge thing, this basin in the middle of it, is probably from an impact. Now, what I was saying before is you tend to see a crater on a moon that's about, a certain percentage of the size of the moon. You never see them any bigger. And the reason is because if you have an impact from an asteroid, say, hitting a moon, if you had an asteroid impact big enough to make a crater bigger than that, it's going to shatter the moon. So you have kind of an upper limit on how big a crater is going to get before you don't have a moon anymore to have a crater on. And so you see this a lot on these moons, and I'll show you a couple more in a minute. This one's way bigger than you expect. How? How did that not shatter the moon? Let me tell you something. If you have a box, let me ask you something. If you have a box filled with styrofoam peanuts and you hit it, what's going to happen? Right? The peanuts are going to fly up and fly back down, but they're going to absorb that energy from your impact, from your hitting. If I tried to do that with, if I had a hammer and I hit a block of glass, it's going to shatter. If I do that with styrofoam, it's just going to just fluff around a little bit and be done. So basically, the moon absorbed a lot more of an impact than a rocky moon could, made this immense crater, and it's as far as the ratio of size of crater to body, it's about as big as you can get. Way bigger than most other moons. And if you look up there, there's like black stuff in the craters. What's that? And it turns out the answer is goo, if you don't want to be technical. The technical answer is it's called a tholin. And this is a funny kind of chemical. It's a molecule that's mostly carbon, and it's created when sunlight, ultraviolet light from the sun, hits methane. And methane's a very simple molecule. It's just a carbon atom and 4 hydrogen atoms. Ultraviolet light hits it, blows the hydrogens off, and then the carbon atoms like to combine with each other. And there's a lot of methane, a lot of sources of carbon on these moons. Sunlight hits them, breaks up the molecules, they reform into these long, complex carbon chains, which are dark. And some of them are black, like this one. Sometimes they're red. If you've seen pictures of Pluto and it has those red spots on it, same sort of process, but the different chemical outcome. And so you see this a lot in the moons, and we'll get back to that. So that stuff collects and pools down in the bottoms of the craters, and that's why they look black. So like I said, bizarre. Nothing like that happens on Earth or our moon. And everything about Saturn is alien until it starts to look a little familiar. And some things will happen that way. For example, we are now approaching Titan, the aptly named moon Titan. It is the second largest moon in the solar system. Only Ganymede is bigger, Jupiter's moon. Titan is easy to see with binoculars from Earth. It's that big, about 5,100 kilometers across. That is roughly the same size as Mercury. If Saturn weren't there, Titan might be called a planet on its own. It's that big. You will see that you don't see any craters on it, and that's because it is the only moon in the solar system that has an atmosphere, and a thick one. The atmospheric density is something like twice as much as Earth. So if you were to grab a bunch of Titan atmosphere and bring it to Earth, and you filled it in a balloon and let go, it would fall to the ground. It wouldn't be able to float because it's denser than the air around it. It's very, very cold, right? It's a zillion degrees below zero there. It's very cold, but it's a nitrogen atmosphere, and nitrogen is able to stay gaseous even at these temperatures. Well, that's weird because Earth has a nitrogen atmosphere. We tend to think of it as being oxygen, but oxygen is only about 22%, 78% nitrogen. So our atmosphere is mostly nitrogen. Titan's atmosphere is mostly nitrogen. And there's also carbon dioxide and methane in there and a few other things. It's also opaque. Our atmosphere isn't opaque. I can go out at night and see the stars when it's clear. If you were on Titan, you wouldn't be able to. It would be like thickly overcast. The difference here is those tholins again. There's a lot of haze in Titan's atmosphere because the sunlight hits it, breaks apart those molecules, and they form other things that float and become basically a haze layer. You may be familiar with haze layers in Maryland, I believe. Grew up in this area, and I know what summers are like, and you get that sort of pall of white nastiness in the sky. It's kind of like that, except much thicker, and it's opaque. So you can't see what's going on the surface of Titan unless you don't use your eyes to see. The atmosphere is opaque to the kind of light we see, but other kinds of light can pass right through that without any problem, like, say, radar, which is radio waves. So if you have a radar device on your spacecraft and you look at Titan with that, you see this. And remember, the first time I saw a picture of Titan, I thought, well, that's Mars. It looks a lot like Mars, except it's green. But no, this is a radar map of the surface where you beam radar, just like a cop will beam radar at a car to get their speed. You can do that and map out, excuse me, I have gotten ahead of myself. This is not radar, this is infrared. For those of you keeping notes at home. I jumped ahead a slide and I apologize. Infrared light can get through haze. Firefighters use that to see through smoke in a burning building, for example. And so when you have a camera that's sensitive to infrared, you start to see some surface details. Along the equatorial region of Titan are these darker regions that are dunes, but they're not sand dunes, they're dunes of hydrocarbons, not carbohydrates. Don't get that backwards, or else you're going to be the wrong kind of oil, I think. Olive oil is a hydrocarbon, motor oil is a carbohydrate, or I just got that backwards. See, this is why you don't do stuff like this extemporaneously. Don't make up stuff on your feet, Phil. It's hydrocarbons, so it's like oil, methane, ethane, that sort of thing. And it's frozen at these temperatures, and it turns into rock. And so there's an atmosphere and wind. These rocks grind together and form tiny little grains, and then the wind piles them up into dunes. And so that's all basically sand dunes on the surface of another world. Now, you can map Titan with radar as well. And you do this because if you can send a little ping of radar, just a little burp, like just a short burst of radar, it travels from the spacecraft down to the ground, bounces back, and goes back to the spacecraft. And if you time how long that takes, you can measure the distance, because we know the speed very well of how fast light travels. So if you know the speed, you know how long it took, you know the distance. And the thing is, if you're careful and you measure things very carefully, if it hits a mountaintop and bounces back to you, it takes a little bit less time than if it hits a valley and bounces back to you. So by beaming radar all over this moon, you can make a 3D map of it and see all the valleys and mountains and everything. And it turns out there are highlands on Titan near the North Pole. That's what all these are. These are ridges and hills and all that sort of thing. But then, when the first astronomers did this, there are these black regions. That means they're not, whatever that stuff is, doesn't reflect radar. It's just black. You're just not getting any signal back. What doesn't reflect radar? It turns out the answer is liquid. Liquid doesn't reflect radar. It absorbs it. Well, what can be liquid at Titan's temperature? Water is frozen so solid it's harder than granite. If you had a rock of water ice on Titan, you could hammer away at it. It would be really hard to break it apart. So what could this be? And it turns out the answer is ethane and methane. Very simple molecules that on Earth are a gas, unless you compress them. I mean, liquid natural gas is basically compressed methane. But on Titan, just sitting out, it's so cold, it's a liquid. And so what you're looking at is a lake of liquid methane on another world. That's amazing. But it gets better. Look at all this stuff. Look at this. You've probably seen pictures of Earth that look like this, right? I live in the mountains. I can tell you this. It rains, right? Water evaporates from lakes in the ocean, right? Rains down on the mountains. You form creeks. The creeks come together, and you get bigger creeks, and they come together to form rivers. And those rivers flow into lakes or the ocean or whatever. It's called the water cycle here on Earth. You probably remember this from third grade Earth science. That's what's happening here. There's a methane cycle on Titan. The methane evaporates off these lakes. It rains or snows out on the mountaintops, and it melts and forms creeks and rivers and flows back into the lake. On Earth, the water cycle may be partly responsible for life on Earth. It brings water where there isn't water otherwise. It mixes up minerals along the way, sediments and stuff, lots of things that things can eat, and you get life that evolves and feeds on that kind of stuff. And here you've got the same thing, plus loads of carbon. We're carbon-based, right? We're carbon-based life forms. And here's all the carbon you could possibly want. So could there be carbon-based fishies swimming in the Lake of Titan? And of course, on our spaceship, we know the answer. But again, I won't bore you with the details. Okay, next moon coming in. This is Enceladus. This is an interesting moon. It's tiny. It's like 300 kilometers wide, so not very wide at all, 200 miles. It is almost completely solid water ice on the surface. It is extremely reflective, very easy to spot actually through a telescope despite how small it is. Because it's so reflective, sunlight hits it, reflects off, and it's quite bright. The interesting thing about it that you might notice at first is that it's got a few craters on it. But if you remember, like Hyperion was just loaded with craters, so is Iapetus. What's going on here? Why doesn't this have a lot of craters? It turns out the important thing to notice are these stripes here called the tiger stripes. And when I first heard that, I thought it was because it was like a tiger clawed the moon, but no, it's like tiger stripes. I'm an astronomer, not a zoologist, so you can't blame me for that. And it turns out they really are sort of gorges or cracks. They're called sulcus. Sulci is plural, which means basically valley or something like that. And astronomers noticed this. And one day, Cassini spacecraft, which orbited Saturn for 13 years, was passing by Enceladus and was approaching it from the night side. So it's approaching sort of, Enceladus is dark below it, it's night. The sun's over on the other side, and there's just a little crescent of lit landscape that it could see. And when the picture got back, it showed this. Those are water geysers. Water erupting from the surface along those cracks, the tiger stripes, and shooting out into space. Not into air, but into space. There's no air there. And they are hundreds of kilometers high. Some of them actually are moving fast enough that the ice particles can escape the moon entirely, and they orbit Saturn, creating a very faint ring. This was a surprise. Nobody expected this. And it turns out there is a liquid water ocean under the surface of Enceladus. What is happening is you've got this moon. It's basically a gigantic ball of ice. As it orbits Saturn, sometimes it's a little bit closer to Saturn, and sometimes it's a little bit farther away. Its orbit isn't a perfect circle. So when it's a little bit closer, Saturn's gravity pulls on it differently than when it's farther away. This is very complicated. It has to do with tides. But what happens is every orbit, that moon gets squeezed and contracted, and squeezed and contracted. And that generates huge amounts of friction on the inside. It's kind of like rubbing your hands together. You rub your hands together and they get warm. All this ice and rock and everything in the center of the moon grinding together as the entire world is expanding and contracting heats it up. You heat up an ice moon, what do you get? Water. Well, it's too cold on the surface for that water to be liquid, but under the surface there is at least huge deposits of liquid water, if not a global undersurface ocean. There's a rocky core to Enceladus, which means lots of minerals, and that's probably where the water, there's probably like water and then a seabed and then the rocky core. So there's, it's going to be a lot like Earth. There could be hydrothermal vents, right? Tectonics going on in the core, blowing out, cracking open the seabed, spewing out chemicals. And on Earth, life thrives at the bottom of the ocean, where it's extremely cold, but these vents are warming it up and spewing out sulfur and all kinds of stuff. That's probably happening here too. If it is, could there be life there? It's an interesting question. We used to always think we'd have to go to another star. There are a lot of spots like this in the solar system where we could have life. All right, moving on. Got one more moon. This is Mimas. Do you remember the ancient movie Star Wars? Does that look familiar to y'all? The Death Star moon. I can guarantee you that every time I post a picture of Mimas on social media, I will get at least one person replying, "That's no moon," if you remember that line from Star Wars. But yeah, so here, this is Mimas. It's 400 kilometers across. Roughly, Colorado would just fit in the screen here. And that gigantic crater, Herschel, I believe it's called, again, that's about as big as it can get before shattering the moon. And there is some evidence that some of Saturn's moons, like Hyperion, maybe even Mimas, in the past did have catastrophic impacts that did shatter them, and then they reformed and then the process started over again. Despite how this looks, it's mostly water ice again. It's just the way the picture's taken. It makes it look kind of gray. But it is the last big moon before the rings. There are much, much smaller moons, but this is sort of the last major world before you approach the rings. So now we're getting to see the rings, finally. At first, the rings weren't really well understood. We knew they couldn't be solid because if they're solid and that big, well, when you're close to a planet, you orbit really fast, and when you're farther away, you orbit much more slowly. That's just how gravity works. If something is solid, then it couldn't possibly last as a ring like that because the inner parts would be shearing off from the outer parts, and it would shred. One famous mathematician, Euler, postulated it could be liquid, but that didn't work either. What could it be anyway, and what kind of liquid could last out in space for that long? And then we realized, oh no, it's made of water ice. Again, these are like 98% pure ice, probably better than you could get out of your refrigerator, and at least my refrigerator, which I haven't cleaned in a while. So it's made of countless chunks of ice. Now remember, despite being immense in its span, the rings are very, very flat, which means these chunks can't be very big. And in fact, over millions of years at least, they keep bumping into each other and eroding each other, right? They hit each other and little pieces fly off and they get smaller and smaller. So these chunks are probably very smooth. They're probably irregular shape, but they're relatively smooth and small. The biggest ones are probably no bigger than maybe a car, something like that. And most of them are far, far smaller. The rings are divided up into different groups. They were sort of named in order of discovery, but kind of, sort of. The bright ones in the middle here, that's the A group. This tan one here near the edge is B, going all the way to the edge. There's C and D on the inside, which are much fainter and were discovered much later. There's this gigantic gap here called, well, this one you can see in the middle there. That's called the Cassini division, named after the astronomer, I believe, he studied Saturn. I believe he discovered that. And there's this other one, this other darker one, which is the Encke division. A lot of names, and they're all named after different astronomers, and it actually gets kind of tough to keep them all straight. And there's even a much thinner one here right by the edge, which you can barely see, called the Keeler gap. And we're going to take a closer look at that in a minute. If you fly over the rings, like the B ring there, it looks like a phonograph record, if you remember those. And judging from the hair, including mine, y'all remember vinyl records. And it turns out that these gaps and these brighter spots are due to the moons. Every time, say, Mimas orbits Saturn slower than the rings do. The rings are closer to the planet. So for every one time, say, Mimas goes around, a ring particle might go around twice. And so it feels this tug outward from Mimas relative to its motion around Saturn every time, every single Mimas orbit. This is called a resonance. So if it's a simple fraction, like the particle goes around twice when Mimas goes around once, or the particle goes around 3 times for every time Mimas goes around twice, these very simple numbers, this particle feels a tug and it moves out of that orbit into an orbit where it no longer has that resonance. And what that leaves behind is a gap. There's just no particles at that space. And the Cassini division is that's not the Cassini division. Cassini division is way down that way. That big gap is actually the 2-to-1 Mimas resonance. But there are other ones as well, and they pull out these gaps. It also helps the ring particles pile up in certain places too for similar reasons. So Saturn doesn't have like 5 rings, like you might guess from the names. It has thousands. The closer you get, the more you see. So here you can see, look at this. Here's a gap. I believe that's the Encke gap. There is a ring in it because right there's no resonance, but on either side of it there is. And so right here the resonance ends, and you get all these cool rings. And then you look at that one, and it's like, oh, what's going on there? This is taken when the rings were edge on to the sun. So if you can imagine standing on Earth, shouldn't be too hard, and the sun is setting, so right, the light's coming flat towards you, right, over the ground, and you leave a really long shadow. So it doesn't matter how tall you are, you can be really, really tall or really, really short. Your shadow is still very long. And so if you take a picture of Saturn's rings when the sun is right over the rings, any bump will leave a long shadow. And look at that. You see some weird shadows there, and then that one spike of a shadow. Turns out that's a moon in the Keeler Gap. And that moon was discovered not directly. It was discovered because of its effects on the rings. And then it was seen by the Cassini probe, which then got a close-up look at it. And you can see it there, that little pecan spud. That's called Daphnis. It's, I want to say 8 kilometers long, 5 miles. That's big, right? 5 miles is like Mount Everest. It's big, but it's tiny for a moon. That gap is only about 20 kilometers wide. You're seeing this at a funny angle, so the perspective's a little off. But it turns out Daphnis has carved that gap in the ring. Any particle that's orbiting near Daphnis is going to feel its gravity, which is incredibly weak, and get pulled toward it and fall into it. So it may have started as just like a little clump of ice, but over time it got bigger and bigger as it attracted more and more stuff. And now here it is. What's this? Yikes! What is that? This is so weird. You're driving on the highway. You're driving it, I'll use imperial units. You're driving at 60 miles an hour. Somebody passes you at 61 miles an hour. Now, if I'm standing on the side of the road, I see those two cars going past me really quickly, and I'm sorry to have scared the AV person with a, try to keep my head up so I don't blow out my mic. But to you in your car, you see that person passing you at 1 mile an hour, right? Speed is relative. It depends on where you're sitting. Well, if you're sitting here with Daphnis, you're sitting on Daphnis orbiting Saturn, it feels like you're not moving. But the particles in the rings that are closer to the planet, they're moving faster than you. They're going to pass you. And the ones on the other side are moving slower, so you're going to pass them. And the thing is, that takes a long time. Even though these guys are whizzing around Saturn in just a few hours, they're moving really fast, they're going around in a circle relative to each other very slowly. And so if I'm a particle on the inside of the ring, let's see which way this is. I want to say Saturn's that way, but I'm not 100% sure. So if I'm a particle on the inside of that gap towards Saturn, and I see Daphnis over here, I'm moving a little bit quicker, and I see Daphnis coming up on me very slowly. The thing is, Daphnis doesn't orbit exactly in the rings. Its orbit is a little bit tilted. And so what you're seeing is you're starting to pass it, but you see it moving up and down very slowly like this. And so I feel this sort of up and down motion as this thing, and as it passes me, maybe it pulls me up a little bit and then back down, and you wind up getting a ripple in the rings. And so you get that ahead of Daphnis because you're moving faster, so you pass it, and that effect makes ripples moving ahead of Daphnis on the inside ring. But on the outside, it's the opposite effect. Now, Daphnis is passing you, and you don't feel that up and down until it gets to you. So you wind up getting these ripples behind you. And when you look at that, if you could see that up close, you'd see this. Right? Here's Daphnis, there's Saturn, and on the inside edge, you have the ripples going ahead, and the outside edge, not much, but they would be coming down this way. What? And it turns out, yeah, it's weird, it's hard to understand, and I get it if you can't picture this in your head, because it baffles me. I've given this talk and talked myself into confusion a couple of times. I got it right this time, awesome for me. But that's an amazing thing, and you can see it in those Cassini images. If you were to get up close to Daphnis, you might see something like this. It's a beautiful piece of artwork, actually, where you can see those ripples and the particles getting sort of flung up on the inner ring and then behind it on the outer ring. If you could get into that gap, you might see Daphnis above the rings here just a little bit. It's about as high as it gets. And those ripples here. And now, if you're on your spaceship, you're trailing behind Daphnis. And is this the camera that's on me? Because that's really funny. Hi everybody, I'm too close. Okay, I'll get back here. If you're on a spaceship following Daphnis, and you say to yourself, you know what? I'm in the ring system. What does that look like? So if I see Daphnis like this and I go, turn my ship like this, what do I see? I see that. That's what the rings are going to look like up close. Cassini, which like I said, orbited Saturn for 13 years, never got that close to the rings because you don't want to send a spaceship through that. Imagine, it's moving 10 times faster than a rifle bullet. You don't want to be going through that. You're not going to have a spaceship anymore. You're going to have a very rapidly expanding cloud of vaporized metal. But that's pretty much what it would look like. It might even be flatter than that. But that's, like I said, smooth and irregular, but pretty cool. So now, we've seen the rings up close. We've seen the moons up close. Now our captain's going to take us up and over the planet. So here we see a view you can't get from Earth because Saturn, because Earth is between Saturn and the sun. We can never see the dark side of the planet, or not very much of it. That's the shadow of the planet cast on the rings. And you can only see that by a spacecraft looking down on it. I love this shot for a lot of reasons. But one of them is, too, you see that little pale blue thing right at Saturn's North Pole? Kind of hard to see. If you use different color light to look at it, you get this. Let me tell you how the conspiracy theorists loved seeing that when that image came down. Aliens! Or fluid dynamics. And of the two, I'd rather it were aliens because it would be easier to understand. This is an effect that happens when you have two rotating fluids, like one in the other, going at different speeds. It's very common for them to shear against each other and form regular polygons. This is called a Rossby wave. There are people probably in this audience who could lecture you for hours about this. This is, it's an atmospheric effect, and people here at Carnegie who understand this a lot better than I do. It happens on the Earth as well. We see this in the jet stream, and we see it on Saturn. There's a hint it may be on Neptune as well. But this one's this fantastic hexagon. Each side of this is 19,000 kilometers, I want to say. It's sufficiently wide that you could toss the Earth into this thing without it hitting the edges. So it's enormous. And there's a permanent cyclone in the center there that you can see as well. Totally natural. You can reproduce this in the lab. You can go online and look at laboratory experiments where they have a giant spinning disc and a camera mounted over it. And these two fluids start mixing and they start forming these natural polygons. And it is super cool if you're a nerd, which I am. And I hope you are. And I know some of you are. Okay, so that's the North Pole of Saturn. Now our ship is heading down to the night side of Saturn. And we can get close to the cloud tops. If we could look out our window, we might see this. There's Titan up there in the upper right. It's mostly dark, but the atmosphere around it is still bending some sunlight around it. And you see a ring of the air lit up. But we're over the cloud tops, and we can see the rings and the shadow of the rings. And the sky is bluish. And, well, that's kind of true. There's enough air above where we are right here that it can turn the sky blue, much like it does on Earth. The problem is, if you go down too low, you get into this yellowish layer, which, if you remember, all the pictures of Saturn look kind of yellow. That's a haze layer. If you could get rid of that haze layer, it would look a lot like Jupiter with those really striking dark and light bands and everything. But that haze layer just kind of blows that all out, fades it all out. And so at the cloud tops, that's pretty much what you would see. And if you keep moving onto the night side, the setting sun will light up the clouds orange. We've got some of our spaceship in the way there. And you can see the rings. And this gets to be interesting because if you wait long enough, you'll be able to see the shadow of the planet itself on the rings. Now, mind you, if you're floating in the cloud tops of Saturn, those rings are going around you very rapidly. Excuse me, I said that wrong. The planet is spinning very rapidly. The rings are just sort of out there. You can't see the individual particles, so it just looks like a solid structure, just with all the little gaps and everything in it. So you're just kind of looking at it. But the day on Saturn only lasts 10 hours, which means the entire day-night cycle. Night only lasts 5 hours. From sunset to midnight, it's only 2.5 hours. So you will actually, that shadow of Saturn is going to rise off of the horizon and be up overhead in just 2.5 hours and then set 2.5 hours later. So if you wait a little while, it'll go from this to this. And you'll be able to see that whole thing move across the sky. Now think about this. Saturn's atmosphere is very, very thick. There's no land to land on. There's no there. It's just sort of gas and liquid all the way down. So if you had a balloon of hydrogen, say, hydrogen, you don't want to do that on Earth, Hindenburg. Saturn, there's no free oxygen. So if you had a dirigible made of hydrogen and warmed it up, it would float. You could put a gondola underneath it, seal it up so that the atmosphere can't escape, and heat it up because it's very cold there. And you could take a balloon ride over Saturn. Every day you would see this. Every 5 hours, 10 hours, you'd be able to see this. What a honeymoon idea. Float in the clouds of Saturn. Watch the shadow of Saturn rise and set. Watch these moons go. Name your price. You could, oh my gosh, you can make a fortune doing this. I love that idea. Now we're on the dark side of Saturn. We turn around and we look back, and we're seeing Saturn silhouetted. The sun is off on the other side. There's a ring of light around it through the atmosphere. We're seeing the rings through the other side. And you can see there are other rings here that are much fainter, caused by the other moons, like getting hit by little meteorites and stuff and blasting material out, and possibly the volcanism, like the geysers like on Enceladus. Now what's interesting about this picture too is that there's something right there, a little bit hard to see. I've always wanted to say that. Sector 3G, computer enhance. Oh yeah, okay, there it is. There's some stars here, but that bright object's brighter than a star, right? Enhance again, that's Earth. That is Earth as seen from Saturn. I think, I've never been able to determine this, but I think that blob next to it is the moon. That's over 1 billion kilometers away. That's Earth. Like Carl Sagan said, everyone you have ever known, every human who has ever lived and ever breathed, every king, every beggar lived on that dot right there. That to me is exactly why we do this. Why do we study Saturn? Why do we spend all this money? Cassini cost $2 billion. Every rover we send to Mars is $1 billion. Hubble costs 10. James Webb costs 10. Why do we spend this kind of money? And the answer for me is right there. We look out because we see ourselves when we look out there. We have asked forever, as long as humans have been human in any sense, we have asked, how did we get here? Why are we here? How does all this work? And science has done a pretty decent job at figuring a lot of this stuff out. Mostly with mythology, trying to answer those questions. But now it's like, yeah, now we're getting answers. We're starting to figure out, we kind of know how stars form now and how planets form. And we learned this by building telescopes. We've learned how our planets formed and how they behave by going out there and taking a look. And Saturn has some similarities to Earth. Titan has an atmosphere similar to ours. Saturn has a layer in its atmosphere that's kind of like ours. It's poisonous, but it's at about the right temperature and pressure. Like again, if you were in a gondola, you could easily survive there. You could float in Saturn's atmosphere. We go out and find ourselves. We find things that are similar to Earth. That pentagon pattern is the wind pattern we see on Earth too. We learn about our planet by studying the other ones. We find out what's going on. And sometimes that knowledge is just cool. Other times it's critical. We understand how our atmosphere works. We understand how hurricanes form. We understand how we're changing the climate. All of this sort of thing. We learn more about this by going out and studying the other planets. It's a compare and contrast kind of a thing. And that's why we do this. And that to me is the amount of money we spend on this is a pittance. If the US budget were $1, NASA's budget would be a fraction of a penny. We spend very little on this stuff. And yet look what it gets us, knowledge, wonder, awesomeness, and beauty for that tiny, tiny, tiny fraction of $1. So, if you liked this tour of Saturn, our tour lines also goes to Pluto, the last sentinel of the solar system, a globular cluster where you can watch 1 million sunrises every day, a nebula where stars are born, watch stars being born in front of your eyes, and a black hole, the last vacation you'll ever take. All this and more in the tour book, Under Alien Skies by me. And if you want to get more information on it, you can use your QR code reader, take a picture of that, and that'll take you to my website of How Under Alien Skies is. There are 10 chapters. Saturn was my favorite. But the one I wrote about asteroids and comets also holds a special place in my heart. That is a very, very, if you think this is strange, asteroids are even weirder. So I hope you all can take a look at that. If not, either way, thank you for listening to me blather on about Saturn for an hour. I really appreciate it, and thank you for inviting me here tonight.
Thank you so much, Phil. Awesome. Fantastic.
I think I ran about 5 minutes long, which is
I have-
shocking. For
I
me, that's
have-
early.
We'll take a few questions. I've got, well, I see the hands going up. I've got one on here, and then I'm going to come around to you all. I like this one a lot.
Yeah, this is cool,
This
isn't it?
could
Yeah.
take 10 minutes.
I've seen a few other groups use
How do
this.
the
It's neat.
dynamics of Saturn's rings, specifically the interactions between its moons and the ring particles, inform our understanding of planet formation and evolution of our
Oh,
solar
man.
system? Great question.
Yeah, it's a really good question. So we are pretty sure how solar systems form. You have a big old gas cloud. Oh, wait. Like this, the Orion Nebula, famous nebula. You can see it through a telescope tonight if you stay up late. Huge clouds of gas and dust. They collapse. They flatten out for similar reasons as I mentioned earlier. And the center, the material forms a star, and the rest of the stuff forms a big ring around that star, and then that collects and forms planets. And that's it. Where's my Nobel? It's that easy. It turns out, super complicated process. I skipped a couple of steps. But part of it is that we're not exactly sure how planets form. We think that there are tiny little grains of material that bump into each other and stick and get bigger and bigger and bigger, and eventually you start getting objects which are large, like planets. There's a couple of problems with this process. There's sometimes they get to a certain size and it's hard to make them stick, and there's some other issues with it, but we're, squint a little bit and wave your hand, and that's how planets form. But it's very complicated. I mean, right? Some people here may actually study how stars form in the audience here. It's not that easy, sadly, and it's hard to get in a lab and do this because we have this inconvenient gravity, which is nice. It holds the air down and we can breathe, but it's inconvenient for a lot of science that you want to do. You can go out in space and perform experiments in orbit, and some people have done that to see how like little pebbles stick together. But it's still really hard, and you can't do it on big scales. So Saturn is this gigantic laboratory experiment. Here is a system that looks a lot like what our solar system did when the sun and the planets were forming. And so these ice particles can collide and do things together and stick together. We think we have seen little tiny moonlets form in the rings. There was one called Peggy. It was, I believe, an engineer, a scientist named it after his wife. I can't remember. But it got to a certain size, about 100 meters across, and then disappeared. And they think that in that location, it may have grown by having particles accumulate, but then something hit it and blew it apart. It was in some Cassini images, and then it disappeared. So maybe that's how that works. We're not exactly sure how all this works in detail. And by studying Saturn, that's exactly what we can learn, especially as these moons form and affect the material around them, because that's when things get really complicated. Jupiter grew really quickly. The Earth grew much more slowly because of the gravity differences. How? Why? How does that work? And it turns out by studying Saturn, that can give us insight into those processes.
Okay, well,
That's
take
a great question.
couple questions here.
Who has the cube?
You explained to us that you could tell your spaceship pilot to move here and there around Saturn. Since it is a gas planet, could you just tell your pilot, hey, let's fly right through Saturn? And if you went into the clouds, would you find anything? Is there anything interesting underneath those clouds? And why haven't we sent a probe? If it's just gas, why can't we explore beneath the clouds?
There is interesting stuff there because in science, everything is interesting. That's not true. Most things are interesting, I should be honest. But I wouldn't recommend that trajectory necessarily. First of all, it's not gas all the way through. There is a core, I mentioned this earlier, and it's big. It's 25 times the mass of the Earth. And it is metal and rock and mostly solid. There's probably some liquid in there too. The pressure of the atmosphere above it squeezes that stuff so hard. The physics of that is incredibly difficult to understand. Even in our own core, scientists are completely baffled how that works. I don't even know how they know it's a core. I mean, come on.
That's not entirely true.
I'm making fun of Michael here because that's what he studies. And we tease each other a lot about geology. So it's really actually very difficult to get those kinds of pressures in a lab, especially on a big scale. So we don't know exactly what's going on there, but we're pretty sure that's what's going on. And then above that is this gas. But above that, there's so much pressure that that gas is squeezed into a liquid. And even then, it's not like a liquid like you have, like a glass of water. These liquids have weird properties because they're under huge pressure, and they're very hot. They don't boil because they're under so much pressure, but they're still very hot. And it's only the top few couple of thousand kilometers, I think, that's a gas like we would think about it. So if you were to go down into Saturn, the view would be gorgeous. Then it would be nothing as you go through the haze layer. Then it would clear up probably, and it would start to get dark. But as you go down, the pressure gets stronger and stronger. Just like in a submarine, if you try to go down too far, right? And the same thing would happen. I'm not sure if you would get crushed first or if you would burn first because of the heat. But in fact, that's what happened to Cassini. After 13 years, the mission was over. It did everything it could. They were running out of fuel, and they decided to end the mission. They dropped the probe into Saturn to let it burn up. They didn't want even the chance that it might hit one of those moons because it would contaminate those moons, and some of those moons might have life. We don't know. So they said, you know what, we're going to drop it into Saturn. That thing took data right up until the last minute and then burned up and became a part of the planet it studied for over a decade, which is one of the most poetic endings any of us could hope
Other
for.
questions? One there, one there.
I love this cube. It's a speaking cube.
Of all the images that you showed, were they all photos from Cassini except the one in the middle of the ring
Yes.
with the rocks?
These were mostly Cassini. A couple were from Hubble, and some were drawings. All the ripples when you were in the rings, those were drawn by a friend of mine named Kevin Gill, who's a gifted photographer, gifted artist. He does a lot of image processing, takes images from Cassini and Voyager and other probes and makes these gorgeous images. And I asked him, he had this one gorgeous shot of looking up to the rings. And I showed you Titan with the ring around it and everything. And I said, could you put Saturn's shadow over that and then move it over a little bit? And he was like, sure. I was like, oh, great. And I thought it would take like a week. And like an hour later, he's like, sends them to me. So here you go. I'm like, okay, awesome. Put those in the talk. So yeah, those were generated digitally, not on a computer, not by a computer. But almost everything else, yeah, those were all the moons and everything, those were images.
Hi.
That's what those things look like.
I might ask this for the universe itself, for all the planets, but how does it compare in terms of the amount of elements and minerals that are available in that area? I mean, is it as rich as our planet?
That's a really good question. It turns out we know even early on that Saturn can't be like Earth because it's huge but very low density. And if it's low density, it can't be all rock and metal like Earth is, or else its density would be like Earth. Earth's average density is about 5.5. Saturn's is less than 1. So it's clearly made of something different. And it turns out once you get good enough instrumentation and you look at Saturn, you say, what are you made of? And it turns out it's mostly hydrogen and helium. And then methane and carbon dioxide and ammonia and a few other things. But overwhelmingly, it's hydrogen and helium, which is really interesting because the sun is mostly hydrogen and helium. And the Earth has very little hydrogen and helium. Well, hydrogen and helium are very light elements. And there was plenty of that stuff around when the Earth formed. The Earth may have formed with a hydrogen and helium atmosphere, but it was warm because it was close to the sun. And the gravity of the Earth couldn't hold on to it. So that stuff basically all went away, leaving behind the heavier stuff. Well, Jupiter and Saturn and Uranus and Neptune, and I'm, again, skipping a few steps and simplifying this, but those guys are so far out from the sun that they're cold. They're giant planets. They have a lot of gravity, so they could hold on to a lot of those elements. And those elements are sort of the same ratio that you see in the universe at large. When you take the measure of the entire universe that we can see and say, how much hydrogen is there? How much helium? How much carbon? How much oxygen? You get about the same numbers in the sun. It's roughly 3/4 hydrogen, roughly 1/4 helium, and with a little bit of other stuff polluting it. And it's because that's what's out there in the universe, made by the Big Bang and then eventually stars that scattered this material around. And that's what stars and planets are made of now. The little bit of other stuff, like what the Earth's made of, is a tiny fraction of that other stuff. But we see it here because of our situation. Our situation is different than Saturn's. Warmer, not as much gravity, so our mix is different. So yeah, I mean, that's a great question. It turns out, yeah, it's very different, made of very different things that we don't see anymore
Okay,
around.
one more question.
One more question, okay.
Hey, so it kind of shocks me that there hasn't been an asteroid or something that's actually hit the rings and disrupted them. And so A, why is that? And then B, if that were to happen, would you anticipate the rings eventually returned into that inevitable flat plane?
Oh boy, we have another 20 minutes, right? There is some evidence that some asteroids have hit the rings. There was a thing called a jet. I think that's what they called it. In one of the Cassini images, there was like this finger of material sticking out that appeared one day and then disappeared. And I think they saw 2 or 3 of these. And I don't remember what the conclusion was but the last I read is that it's possible that something hit the rings and, sort of blew out a bunch of the ice. And so that's what you were kind of seeing, is just sort of a plume of stuff. The rings are huge and they're very not solid. I mean, I don't know what the word is for that, right? It's made up of zillions of little particles. So if even a big asteroid, 10 miles across, hit the rings, it's just going to punch a hole in the rings 10 miles wide. 10 miles on that scale is like nothing, right? In those overview images of Saturn, you wouldn't even see that. It'd be tiny, tiny little dot. So yeah, if you had 1 trillion gigantic asteroids hit the rings, that would be, well, it'd be trouble for a lot of reasons, probably not just because the rings would be gone. But something I mentioned earlier about Iapetus having rings, but we don't think Saturn's rings have been around forever. It turns out with Cassini, we could measure the mass of the rings, just basically how much stuff is in them. But you can also figure out a few other things, like as little tiny particles out in the solar system smack into the rings, they're called micrometeoroids. So you think of them as like little tiny meteors. Hit the rings, they leave like a dust layer behind. And the amount of dust you can measure tells you how old the rings are, because it's just like if you walk into a house and there's an inch-thick layer of dust everywhere, that place hasn't been dusted in a long time. And so the more dust there is, older. Same thing. Also, we know that the ring particles are raining down onto Saturn. On the inner ring, the edge of the inner ring, those particles are moving down and raining down. And when you look at all these processes and combine them together, you can calculate how old the rings must be now and how long they will last. And the answer you get, depending on the math, is very roughly 100 million years they've been around. I've seen some estimates of 400 million, but I don't think those are accepted as well, as about 150 million. So as a friend of mine points out, if you were a dinosaur in the early age of the dinosaurs and you had a telescope, you'd see Saturn without rings. So Iapetus might have had rings before Saturn did. And if you came along in a couple 100 million more years, those rings will be gone. And what's very interesting about that is, call it 500 million years, that's still only 1/10 of the age of the solar system. The solar system is very roughly 5 billion years old. So it's kind of a coincidence. There's a 1 in 10 chance that we happen to see Saturn with rings, and the other 3 gas giants have rings, but they're not as magnificent, which makes you wonder, that's a pretty big coincidence. Does this happen a lot? Maybe this is a process that happens every couple 100 million years, and to Jupiter, to Saturn, to whatever, and you get these magnificent rings and they just go away. Jupiter may have had rings like this, but they're gone. We don't know, but it's kind of wonderful to think about that. And as we're discovering more planets around other solar systems, gotta wonder how many of them have rings. Saturn is gorgeous and it's an exceptional planet in our solar system, but there may be a lot of them out there. We don't know.
Fantastic. Thank you so much.
Thank you. Yeah, sure. That's a good question. It's going to be clear for the next week or two, too, I hope. Yeah, there's a new comet. It's fallen in from the outer solar system. And it's got a Chinese name that I have not actually ever said out loud. I've only read it, so I don't think I could pronounce it. It was discovered at the Purple Mountain Observatory, which in Chinese it's Xuanxin, can't remember, dash Atlas. And Atlas is an observatory in Hawaii, I think, and they co-discovered it. And it's passing the sun very soon in the next few days, October, I think actually soon, very soon, the next couple of days. And what's that? Yeah, believe me, oh God, don't watch TikTok about this comet. That's all you're going to see. It's actually very close to the sun right now. It's going to whip around. It's not getting anywhere near the Earth, but it's looking like it's going to be very bright. And it's going to appear in our skies after sunset around the 12th or the 13th, so in just a few days. And nobody knows how bright it's going to be. It's already naked eye visible. And I have a lot of friends who have seen it in the morning from Australia because it came in from the south. And then it's going to pass us in the north. So we're going to get a good view of it here. So if you get a chance to see it, take a look. It'll be in the west after sunset. Just go online, look for really bright comet, and trust me, you'll find a million websites about it.
Thank you
So
very
hopefully
much.
be able to see it. And that's only one comet. There's another one too.
Oh, really?
That made it brighter. Yeah, nobody knows. Exciting. That was fun.